Hey, what's up guys? My name is Cherno. Welcome back to my game engine series. So last time we finally actually used shaders to draw a triangle properly, and that should have worked for everyone. Today we're going to talk about something that we haven't talked about thus far. We kind of just wanted to get everything up onto the screen as quickly as possible, just having kind of raw OpenGL code right inside our application class. And today we're finally getting to discussing kind of the design, the abstraction of these kind of rendering API calls that we have currently with OpenGL, and how we're actually going to handle multiple rendering APIs, because that's a pretty big issue that really needs to be addressed when you're thinking about game engine design, especially if you want to actually have some kind of rendering engine that supports multiple APIs. It's kind of two big kind of abstractions that go on in game engines usually to do with kind of multiple platforms, and that is the multiple actual platforms, right? So stuff like Windows, Mac, Linux, Android, iOS, PS4, Xbox, Switch, whatever, those kind of abstractions where you're actually dealing with different platforms. And there's also the rendering API abstraction, in which you're dealing with the potential for rendering APIs that it actually, for basically supporting multiple rendering APIs. So being able to render using Directx, using OpenGL, using Vulkan, any of that kind of stuff. So both are very big discussions. Obviously, we're going to be talking about rendering APIs today. And I also want to kind of say that there's a lot of schools of thought on this. I've seen in my professional career, I've seen a lot of different ways of doing this. The way that I like doing it and the way that we're going to do it for Hazel is just one of the many ways. You don't like, there's no correct way. It depends on what kind of suits your needs and what you actually like and what you want the API to look like and what you want the code to look like. Programming and just, writing code is such a subjective kind of thing. I mean, yes, there are objective truths as to, sure, you could do it this way, but it's like technically on paper worse in every way. Like, sure, the code might look pretty, but the performance is bad, the abstraction is bad, the API is terrible. Well, I guess if the code is pretty, the API wouldn't be terrible, but you get my drift. I'm a big believer of doing things like properly, in the sense of, yes, the code might be harder to read and it might not be as nice, but it is going to perform faster. Obviously, me coming from a background of like game engine engineering at EA, we definitely care about performance because we're trying to push the limits. So it's important to kind of consider that, and that's kind of just who I am as a programmer. I really care about performance, and I like to kind of do it that way. Anyway, I don't want to blabber on forever. I want to give a huge thank you to all the patrons that made this series possible. Patreon.com/the Cherno. If you guys sign up there, you'll get videos early. You'll get access to the source code, to the Hazel kind of development repository, the development branch, which I'm working on pretty much every day. Well, not every day, but almost every day. Last video, I actually showed like a bit of a tour of what the Hazel engine actually is in the development branch, and that was like a huge kind of little kind of show and tell that I did. If you guys are more interested in that, I noticed that some people wanted me to like make a video actually showing the engine, like a standalone video, just kind of like a tour of what we actually have in the engine runtime and what everything, what it can actually do, like all the features. If you guys are interested in that, definitely leave a comment below. But if you want access to that, like right now, you can just sign up on patreon.com/thecherno, help support the series, and you'll get access to that source code and to that build. Okay, so anyway, back to this. Let's talk about rendering APIs. How do we support multiple rendering APIs? So I think the biggest choice that you have to make here is if you're going to kind of have this support during compilation or during runtime. So I'll kind of talk about like what I mean by that. Essentially what you could do, right, with multiple rendering APIs is you could say that at compile time, when I physically compile my code, right, you need to select a rendering API. For example, I want Directx. And then what will happen is, via like essentially ifdefs or certain files that are either compiled or not compiled based on your kind of configuration setup here, you can basically choose that like, I am going to compile with Directx, meaning that Hazel's going to be built with Directx, right? If you want OpenGL, then at compile time, you choose OpenGL, right? And then all the files that are compiled are kind of OpenGL specific, right? And then you get OpenGL into your final build. That, and to give you a more practical example, what I mean is like, you could have like essentially a file for each kind of, you break down the rendering API into primitives. So you have like a Vertex Buffer, an index buffer, texture class, shader class. And then what you do is you have like an OpenGL shader class. And then you have a Directx shader class. And only one of those will be compiled, right? And the one that gets compiled depends on your configuration setup, which depends on which rendering API you've actually selected. So you can kind of do it like that, right? Or you could even just have a shader file, shader.cpp, and then just if defs that kind of just says, if Directx is defined, then compile this chunk of code. Otherwise, if OpenGL is defined, compile this chunk of code, right? That's another way to do it. Same principle, right? It's just instead of breaking it up into multiple files, you have everything in one file. Sure. So let's talk about the advantages and disadvantages of that. Okay, so the biggest disadvantage, we'll start with the disadvantages because I think that's kind of the glaring obvious one, is you need a separate build of Hazel, a separate physical binary build in order to actually select which API you want to use. And once you compile your code with that API, that's it. You have to recompile the whole engine, or at least the rendering component of the engine, right, the whole renderer, if you actually want to switch rendering APIs. So picture this, right? Well, I mean, we're working and we're like, we've written this game in we're just working on this little sandbox project. We've written it in OpenGL. Suddenly I want to see what it looks like in Directx. Hold my beer while I compile my entire code again with Directx, right? I'm really not a big fan of that. So apart from development times being kind of slow, especially when you're actually working on the renderer, that's another big thing that people don't realize. You have to make this developer friendly. So what I mean by that is, while you're actually developing the renderer, how are you going to deal with this? Well, I've finished the OpenGL implementation. Now I'm working on the Directx implementation. I need to switch between them, right? I need to switch between them to know whether or not the visual parity is kind of the same, right? Are there discrepancies between the two renderers? Does Directx look different to OpenGL? It shouldn't, right? It should be exactly the same. If it looks different, I've made a mistake. So I'm going to have to go back and forth them quite a bit. But to do that, I need to recompile my code. And yeah, I mean, there's a lot of things you could do, right? OpenGL is done. You could bring out all the rendering code into a module. So it's in a separate kind of component, in a separate kind of module, DLL file, whatever, right? And then if you want to kind of just launch with OpenGL, I mean, you could just, or Directx or whichever one you're using, you could just, switch which DLL file it uses. Sure, but that still means that you need to recompile your code, and it still means you need to do that kind of at compile time, right? Not something we want to kind of do to do with that, right? So that kind of decision falls into kind of those two areas. When do you want to make that decision? Do you want to choose which rendering API you use at compile time or at runtime? Obviously, right now it seems like runtime is definitely the superior one because why have this hard decision that you have to make ahead of time if you can just make it at the very end and still be fine with it, right? And we'll kind of go into that in a minute. But the other thing with this is that the primary benefit of doing it this way is essentially performance, right? You know which API you're using. You compile the whole code base with that API, right? Which means that there's no kind of runtime decisions that ever get made, not even once, that say, all right, well, if we're actually using this API, we need to do this. No, because all that stuff is done offline, all that stuff is done during compile time, and it means that during runtime, your code, your program, your engine doesn't have to make any decisions and waste time. Waste time making those decisions as to which API is currently in use or which one you want to use, right? That's not stuff that actually has to be done because it's already been done ahead of time at compile time. So once it gives you less flexibility, it does potentially give you more performance. Now let's talk about the second half of things, and that is making those decisions at runtime. So what does that mean? What that essentially means is that you compile everything, right? So you have an OpenGL implementation, you have a Directx implementation. Both of those implementations get compiled. Usually the way you do this, again, you could just, instead of if-defs or whatever, you can't really do if-defs because you can't have a shader class that suddenly does both. I mean, if you were really crazy and a big psychopath, you could probably just have inside every kind of function that you have, right? Inside every kind of function that you have for shaders, like bind shader or, upload uniforms or whatever, you could have an if check that says, hey, if it's Directx, run this code. If it's OpenGL, run this code. That's just psychopathic, to be honest. I don't know why anyone would do that, but I have seen that. That's why I'm mentioning it. Don't do that. You could do something like that. Usually you break it up into multiple files and potentially, again, many ways to do this, but potentially if you're doing it at runtime, you'd probably have a base kind of abstract, pure virtual kind of class that has no implementations, probably stores no data at all, just acts as essentially an indirection, an abstraction, if you will, And then you have two classes, or basically one class that breaks off per rendering API. So you might have, shader, and you might have OpenGL shader, and you might have Directx shader. Those are both child classes, subclasses from that original base class, which is that just shader class, right? And then since they're pure virtual, at runtime, when you actually create a shader, you decide upon creation, right? So it's not really like taxing, and there are ways to make it even faster if you want by like pulling your shaders together or doing whatever you want. But essentially when you create a shader, it checks to see what the current rendering API you're using actually is. And if it is, OpenGL, then it creates a new OpenGL shader and returns that. If it's DirectX, it creates a new DirectX shader and returns that, right? But the base type it's returning is the base class type, which is just shader. So all of your client code that's in Sandbox at this stage, right, or inside your game, that just sees shader. That's all it is. It's a pointer, it's some kind of reference to a shader object. But the implementation detail of whether it's an OpenGL shader or DirectX shader is kind of hidden. I mean, usually you would provide ways to extract that just in case, because no engine's API is that kind of complete, really, that you can just do everything you want within that. It's a bit weird. I haven't really seen that before. I mean, it depends what you're doing. If you're doing really simple stuff, you shouldn't need to dig in deep into the implementation details, but you might. So you might have that kind of filtering through. But essentially, the client code just says shader. It doesn't care what shader is, because if you think about it, what does it do? It opens some kind of, creates a new shader based on like a file or something. It binds the shader, it uploads uniform data. It doesn't need to know if you're using DirectX or OpenGL, because that's kind of the API you've defined. In that rendering API kind of video thing that I made a few months ago maybe, I talked about that line, right, between your actual renderer API and then your actual renderer. So the renderer just uses the rendering API. It shouldn't care which implementation you're actually using, which specific renderer you're using. It should just be as simple as just looking up shader and being like, I want to create a shader, I want to upload these uniforms, I want to bind the shader for rendering, right? Simple as that. So obviously there's the obvious fact here that not all rendering APIs are supported on all platforms. So DirectX, we've been talking about DirectX and OpenGL as our two main ones, just for the sake of this example, right? For the sake of this kind of conversation. OpenGL is available on pretty much everything. DirectX is only available on Windows and like Xbox and just Microsoft kind of products. So if you're compiling on Mac or Linux, your DirectX code is not going to compile, is it? No, it's not. So you still have to have like ifdefs or not even ifdefs. The way I do it, I don't usually have ifdefs. I just have separate files. So I have shader.h and maybe shader.cpp, which is like my base abstraction. And then in my platform specific kind of folder hierarchy, I have OpenGL shader.cpp and .h, and then DirectX shader.cpp and .h, right? And DirectX, you don't really need to worry about the header file, but DirectX shader.cpp, that is turned off for like Mac and Linux builds, and probably all builds except for Windows at this rate, right? So that's not even going to compile. It's only going to compile when you generate the project for Visual Studio for Windows, right? If you're targeting Windows, that gets compiled. Otherwise, it does not get compiled. Okay, and header file you don't need to worry about. That way, obviously, and then also usually in your actual kind of generic shader.cpp, you have like some kind of create function, which does a runtime check, and it says which rendering API are we currently using. It's basically like a switch statement. If it's OpenGL, do that. Otherwise, if it's DirectX and you have that block inside ifdefs, then you can return a new DirectX shader. So that way it's kind of protected. It's only going to compile for Windows, that specific code. And I mean, for other APIs, it's kind of the same thing. So you wouldn't really compile Metal on anything except for Mac OS or iOS, right? So you have that stuff either filtered out by the configuration if they're separate kind of CPP files, or if they're in kind of common files, because you do need some kind of link to a common file at some rate in this. Anyway, I've talked a lot. Hopefully this design is making sense. It's really cool to just sit down and think about this. I could draw a diagram of all this. I realize that I usually don't, because I feel like it's just me writing down my words on paper. I think for some people it's good to see things visually. So let me know what you think about diagrams in general. I'll run a little poll maybe to see if you guys want more diagrams. I mean, I do them very rarely. Usually I do them if the video is dedicated about planning or something like that. But the main reason I don't is just because this stuff is, well, at least in my mind, it's kind of simple to the point where everything I would draw is just the words I'm saying. So if you just think about them and maybe rewatch that area if it doesn't make sense to you and just visualize it, not to mention we're about to see the code behind this, so that will act as a visual aid. That's why I don't usually bother, but anyway, I'm always open to feedback, obviously, so please let me know what you think. We have several classes here. We're not going to abstract all of them today, I think. We'll probably do the Vertex Buffer, because I think that's pretty easy. Just to give you guys an idea, and then what I want you to do for homework is actually go ahead and do the same thing with the shader class, do the same thing with the vertex array class, do the same thing with the index buffer case. In fact, I think I will do both the index buffer and the vertex buffer today. Let's jump in and see what we can do. Okay, so this is where we left off last time. If we just run this, then we'll see what we get. So we had this kind of triangle that was kind of interpolating between the vertex position colors that we had here. What we did is we just inside application, we had all this OpenGL code, which obviously is not something that we ever want to keep, right? This is just kind of an example of how to kind of get this stuff on screen as soon as possible. But what we want to do now is make this generic, right? Make this generic in the sense that, you know, I want to just be able to, like, none of this other code has any idea of what a rendering API is, right? It doesn't really, you know, it's got layers, it's got event dispatcher, it's got stuff that is not render API specific. Instead of creating stuff like this and having GL code here that, for example, defines our vertex buffer, what I essentially want to be able to do is create a vertex buffer, right? Which essentially, you know, and the way you do this might be different depending on how you choose to implement it, but, you know, we'll probably want to do something like vertex buffer create. We'll probably want to take in, you know, the vertices like this, maybe the draw mode as well, like the memory storage type, because whether it's static or dynamic or streaming or anything like that. But essentially we want to probably take in the whole kind of vertices definition that we have here as a vertex buffer, and that's kind of it. And then when it's time to draw, we just probably do something like vertex, like buffer.bind, and that's done. We want it to be like this because we don't actually want to include GLAD or anything like that. This could be using Directx for all we know. And this kind of way of doing things, and obviously we don't just have the OpenGL code inside Vertex Buffer. It returns an implementation of which API we've actually chosen. And we'll actually create all of them right now and see what that looks like. Okay, cool. So that's kind of the goal. Usually this would return some sort of pointer. I usually just like returning a completely raw pointer in here, right? And then it's going to be up to, like, if you do have an engine with reference counting or something like that, I would probably return a ref. Since we don't have that at the moment, I'm just going to have create return a raw pointer, and then it's going to be the client's job to actually manage that however they like, either by shoving that raw pointer into like a shared pointer, or usually like what we're going to do here is just kind of putting it into a unique pointer. Okay, so let's take a look at how we can do something like this. This is kind of the goal for the API. So over here in renderer, I'm going to make a new item, and I'm actually just going to call this buffer.h. Now, you might be like, well, okay, is this going to be the vertex buffer? Why are you calling it buffer? The reason I'm calling it buffer is because I'm not a huge fan of creating a million files. I think that it's not that necessary. I think that it slows down your build times. It makes code harder to read through. If you want to like share your code with someone, you have to give them a million files. It's just a bit annoying. So I definitely like creating more than one file. You can see I've actually got quite a few here. They might get collapsed in the future, but probably not. But for things like buffer, I don't really like having a vertex buffer and index buffer kind of class. They're both buffers, they're just different types of buffers. So you should just have them in kind of one file. This is clearly just my opinion. Feel free to disagree with it, but that's kind of what I do. Okay, I basically like to create code like this and then just have multiple classes in one file. It just makes it easier. Okay. And then, you know, I'll do the same for textures, for example. So there'll just be one file per rendering API called like texture, essentially. And then in there, we'll have 2D textures, you know, 3D textures, cube maps, that kind of stuff. Everything to do with textures, kind of all in one file, instead of having to have a separate file for each kind of type of texture, because that's just annoying, in my opinion. Anyway, so we have both of these. We'll include our PCH. We'll include our buffer class. And then our header file, and then we'll have namespace Hazel. And then let's talk about what we need here. So this is our pure virtual interface, right? What I mean by that is there is no implementation here and there's absolutely no members, no data members at all. This should take up 0 storage. Obviously it'll take up 1 byte when we initialize it because it has to, it's a class, but it's got no members. It takes up no storage. It's literally just like a vtable of just functions, of just virtual functions that get dispatched to whatever kind of subclass actually realizes this implementation, right? This kind of abstraction. So we don't really need a constructor or anything like that. You do need to have a virtual destructor. Usually this is just empty, right? We'll do this straight away, I think, for both of these so you kind of get the idea of how it's implemented. And hopefully by implementing it twice, as I am here, you'll kind of see what you need to do to implement the stuff for shader. And then we just define the interface. So Vertex Buffer, what are the functions of a Vertex Buffer? Well, we definitely want to have some sort of like binding function. So virtual void bind, right? We want to be able to bind a Vertex Buffer for rendering. Or if we want to put it into a vertex array. The way that this will actually work with the vertex array, by the way, we will talk about that later because that's a bit different and that is actually a bit more API specific. Unlike, you know, Directx, for example, which deals with this stuff differently. So bind, unbind, I definitely like to have some kind of like set data, upload data thing. So virtual, if you would write it, you do like virtual void set data, and then you'd have your stuff here. And now finally for the construction, what we actually want to do, as you'll notice, is, if I can find where this stuff is, we want to actually, you'll see that what we kind of want is the actual vertex data, right? Vertex attribute pointers as well, something to do with vertex arrays, not really something we want to do right now, but just this kind of chunk of code here, we need to actually give the vertices to this. That was completely the wrong thing, to this, right? However, I don't want to create a constructor because if I create a constructor, that means that I need to I can't kind of choose which type I want. So what I'm actually going to do is create a static vertex buffer. And again, that's what I said, we're returning a raw pointer. It would be like maybe some kind of ref if you had a reference counting system inside your engine, which we don't at the moment. Static vertex buffer create. And here, this is like my constructor. So I take in everything I want here, right? And it's static, so it doesn't actually belong to this class. Vertex buffer create, and then I'll probably just take in my vertices, and then a uint32t, which is my kind of size. Could just use a size t, by the way, but we'll use uint32t. Okay, there we go, done. This is very similar in both of these, except this returns a index buffer instead. And we'll probably have a uint32t, which is our indices, right? So we have an unsigned 32-bit integer. We're probably just going to stick with 32-bit 32-bit indices. For now, 16-bit is definitely an optimization you could make in the future, but more often than not, if you're trying to render things and you're trying to just have a simple implementation, just 32-bit is just the way to go. Otherwise, you'll just run out of indices. Okay, cool. This looks pretty good to me. Now we just need to create these two create functions. So they're pretty easy. We just drag this over here. This is going to be vertex buffer create, right? And then we do the same thing. I'll just use Visual Assist here to make this implementation for me. We've got this here, wonderful. Now what we need to do is actually decide in this function, in this create function, we decide which API we're currently using. So what API our renderer is using, and thus which class type, which actual kind of class we instantiate and return, okay? It's gonna kind of obviously cast it to the base type here, so we're not returning the actual derived type, but that's the intention. Cool, okay. So in order to have classes to return, we actually need to make them. So since we're kind of dealing with OpenGL for now, inside platform OpenGL, I'm going to add a new item, and this is going to be called OpenGL buffer.h. So you can see that everything that is kind of OpenGL related, I'm starting with the OpenGL kind of prefix here. And then buffer is kind of the type of class, or rather the file name of the class inside the actual kind of generic renderer. So we add this, which is the rendering API. We have our namespace. We include the file from the generic kind of rendering API, which is this one, right? And then we make our OpenGL Vertex Buffer class, which is a Vertex Buffer, okay? And then what we do here is we actually implement that file, right? So that class that we've created, we implement it here. So we don't need the create, obviously. So we can take this, we can put it in here. We can keep this as a virtual destructor just because it's already virtual, and this way we know that it is virtual and it's marked correctly. And then bind and unbind, which by the way, I should have made const. And this stuff we just kind of implement over here inside our implementation, which is the OpenGL Vertex Buffer in this case. You can put anything else you want here, right? So obviously we're going to put a renderer ID. Did I make render? I don't even remember. Yeah, well, no, I didn't. It's just a uint32. Usually I'd make a renderer ID type. We'll talk about that in another time. In the shader class, we just had a render ID. So we store this, you'll note, we store this in the actual implementation. We don't store anything in here at all. We shouldn't store anything here, right? This is just an interface, just should not store any data. This is where the data is actually stored. So we have a uint32t, which is our render ID. We'll make an OpenGL buffer CPP file, OpenGL buffer.cpp, which will include our PCH, and what we can do here is just, and one thing that I definitely want to make is a constructor, which takes in exactly what our create function takes in. So inside buffer, we had this create function, which takes in vertices and size. That's what I want the constructor to take in, okay? Vertices and size. Now let's create these implementations using Visual Assist, who, by the way, I'm not sponsored by. I just like using it. And then over here, we're going to do some things. Okay, so first of all, I mean, look, this is a Vertex Buffer class. We're currently drawing a triangle. In a game engine, a Vertex Buffer class is quite exhaustive. It's quite big, right? There's a lot of decisions you want to make, such as whether or not you retain this vertex information on the CPU side, which you might want to do if you're doing things like ray picking, or ray casting to mouse pick, stuff like that. There's tons of different, like collision, whatever. There's tons of different things that you actually might want to do from a Vertex Buffer. What we'll do for now is we'll probably won't retain this, at least we won't copy it and keep it here. But what we do need over here really, I think is, well, I don't know. I mean, we don't really need anything, to be honest. The size and all that stuff we'll handle in the constructor. So this is the actual code we have here, and we're still using gen buffers, not create buffers, but that's okay. We could probably just switch, to be honest. I can use something called gl create vertex buffers, or gl create buffers, right? Which is basically these two steps in one. And I don't remember the function signature. I think it's just that. We'll need array buffer in some case. I don't know. I'm just gonna look this up. So create buffers, glad create buffers. There's the function signature. Okay, cool. So it actually does just have the buffers and a size. Okay, so back here, we have our size and we have our renderer ID. All right, cool. We also need to include glad.h. And there we go. So we create our buffer. It doesn't matter what kind of buffer it is at this stage anyway. When we actually set our buffer data though, that's when we will use array buffer for vertex buffer and element array buffer for index buffer. So we can't use size of vertices anymore, obviously, it's just a pointer. We use size, we use vertices, and for now again, hard coding this to static draw. Okay, so there we go. Then we'll also have in the destructor, which we haven't, let's see. So this needs to not be implemented here anymore. We need to take this and implement it here. And then this will just gl delete buffers because we don't want to retain that. Gl bind buffer. Let's see, so gl array buffer and mrender ID, and then unbind, which we probably will not use that often, but we will unbind it there. Okay, cool. So there we go. Very simple class. Just simply creates buffers, uploads them, and then we can bind them for rendering and it'll do all of that kind of stuff. Okay, so back inside our application class, let's try that out and see what happens. So we still have our vertices. We don't need to generate this anymore. If I go back to here, we can, instead of having unsigned in vertex buffer, we can get rid of that and actually have a unique pointer to a vertex buffer. And that will be our vertex buffer. Cool. So then over here, and I'll have to include this. So basically the same as that, except vertex buffer. So now over here we have vertex buffer. I like to just use reset. Is that what I used last time? Yeah, I did. And then we put this in here. Obviously we have the data first and the size second here. That should be okay. Okay, that clearly didn't work. Oh, sorry, it's not vertex buffer, it's just buffer. Okay, and there we go. And then that's kind of it. I mean, we probably should bind it. I'm actually not sure if create binds it or not. That's kind of the problem. I guess we can run this and see what happens. But yeah, that'll be interesting. I don't think we're doing anything else. Oh, we're still doing buffer data. So I shouldn't actually do that. Let's just cancel that build. Oh, it failed anyway. Okay, why did it fail? Okay, so create, of course, create does nothing yet. We haven't sorted this out yet. So what you actually should do is, we don't have a renderer class, which is kind of annoying. We should definitely set that up next time because we really need to, because we also have kind of generic renderer commands like clear and clear color that, you know, in most cases you could probably associate to a frame buffer, but also useful functions to have inside your actual renderer as renderer commands. And inside that renderer class, we'd probably have a switch for the API, right? So if you're using like OpenGL or Directx, it would the renderer is what should kind of have that for you, right? So what we'll do right now is we'll create a renderer class, which is just called a renderer. Right, this is going to be so brief for today, but basically what it's going to do is have an enum class renderer API, right? And then this is going to be none, which is like if you're running headless or if you just don't want to have, if you're maybe doing unit tests that don't require rendering and you're running them on like a build machine or something like that, which might not even have a graphics card in it that you want to test with. So you have none, and then you have OpenGL. And then in the future, you know, we'll probably have like Direct3D or Vulkan or whatever. But these are kind of the two that we obviously have right now. Okay. This needs to be stored in some kind of static state, probably. Again, since I said it's going to be really brief, essentially what we're going to do is just have a static renderer API inside the renderer class, right? Which is the S renderer API, we'll just say. Okay, and then inside the CBP file, which I'll now have to create, since I chose to do it this way, which is fine, renderer CBP, we'll include our PCH, we'll include our renderer.h, namespace Hazel, and then this, for now, clearly something that we can set at runtime, but for now, this just gets set to renderer API OpenGL. Okay, so we're hard coding it here. Obviously, it's something that you could definitely set at runtime. In fact, we're going to add a getter for it. So we'll have inline, this will be public, private, inline render API. I don't know. Get render API. Probably just get API. To be honest, clearly inside the renderer. You could call it current API or whatever. And then this will just, this will be static. And it will just return sRender API. Okay, cool. And then you could also do set API that does the same thing if you want to set this. And obviously if you set it before you create the renderer and the context and the application, essentially before you create the window and everything, it should use that chosen API. Okay, cool. So now that we've got that inside our inside just our buffer class, which is over here, we will include, we're already in here, so we can just include the renderer. And then we do a switch statement and we check renderer get API, okay? So if it is none, then we'll probably won't return anything. So return null pointer for now. We probably will have an implementation that does nothing though. Otherwise this code will crash. So we could just assert in this case, to be honest. We might do that. hz core assert false. And we'll say render API none is not supported. 9 is currently not supported. And then we will return null pointer. And then for OpenGL, of course, so we'll just kind of move this over here. We will, I guess we can move this back a bit. We will return a new OpenGL Vertex Buffer with the vertices and the size. So hopefully this is kind of making sense how this all works, right? And then obviously over here, we return null pointer. And we could just, also have an assert here essentially that says it failed. That's if somehow you set it to a value that's not here. So we can just have an assert that says false, unknown render API. Okay. And then OpenGL Vertex Buffer is of course something that we need to include. So Hazel, where is it actually? Platform. Is platform not inside Hazel? Apparently not. OpenGL Buffer, right? And then obviously, if for example, right, this will shed some light here. If for example we had Direct3D and Direct3D Buffer or Directx Buffer or whatever you called it, right? That since that's Windows only, you would do something like if hz platform Windows or something, you would do this. Otherwise, you wouldn't, right? And that way, you'd still be able to compile this class. On like Mac OS, and then same with this. If this was, DirectX instead of OpenGL, you could surround this case specifically by that, right? And then that way, obviously, the DirectX code is ignored and not compiled at all on platforms that do not support it. Okay, so there we go. That is that. I think that's pretty much it. Obviously, for index buffer, we need to do the exact same thing. So I'll come over here. OpenGL buffer is still the file here. This will be OpenGL index buffer, which has our indices and our size still. Not a class that we've created yet, I guess. But yeah, there we go. Exact same code, right? I just like to tab this across. Cool. So now I will have to create that index buffer, I guess. So if we copy and paste this, we'll call this our index buffer. And obviously it will be an index buffer. If we go to, buffer's not showing up for some reason, but if we go here, we can steal this, copy it, paste it here. It's going to be another long episode. Lucky you guys. Okay, index buffer. Looks good to me. And then if we go over here, we can basically copy and paste this. I'm just going to replace code here from vertex to index. All right. And then obviously we need to get the appropriate code here, which is that. Buffer data, this becomes element array buffer. We might still need to bind it. We'll check that out in a minute. We'll both learn that together, I guess. Indices, and then OpenGL index buffer. We change this to be element array buffer. Everything else stays the same. Okay, cool. And then usually what I like to do is just kind of separate this because it's all in one file and you kind of want to see kind of the, I guess, separation of these two things. So, sometimes I do something like this essentially. And I don't know, the formatting for this varies. I just kind of change it up depending on my mood. But right now, I guess I'll do something like this, which is just our index buffer, and then this will be our vertex buffer. And sometimes I do this in the header file as well, just so that it's super obvious where we have those two kind of implementations. You probably don't need to have like 3 full lines to take this up, by the way, but do as you wish. Okay, cool. So there we go. Ooh, we've got an extra one here because I guess Vertex was too many lines, or rather one more character. Anyway, so there we go. We're missing something because I put this into the wrong spot. Lovely. Yeah, that looks pretty good to me. If we go back to the buffer CPP file, you can check that, make sure this all compiles, and it does. And then back inside application, instead of having that index buffer as just an unsigned int here, we'll have an index buffer instance here. Okay, cool. And then for that to happen, I need to include buffer, which I already am because they're both in one file, which is lovely, nice and easy. We don't need to do this anymore. Instead of gen buffers and all that stuff and buffer data, we can just create the indices and then say mindex_buffer.reset index buffer create indices size. And that's all we need. And size is just size of indices. Now, actually, this is a good point, right? So the point is, do we actually need size here, or should we rather have count? The reason is that you're specifying uint32 indices. You know the size of them anyway, so why not just have a count? And the other thing that we actually do need in index buffer, which I have neglected, is the count, right? So virtual uint32 get count. And then this will just tell us how many indices are actually in this index buffer, which is important for rendering since we want to commonly render all of them. So we'll have virtual get count here, which will return a count, count, and then uint32t count, right? And then over here, when we take in the count, we'll set count so that we can do this. And then this becomes count times size of uint32. Okay, so that's how I like to differentiate between what is in bytes and what is not in bytes, right? If it's count, then it's not in bytes, it's in elements, which means that you need to multiply it by the size. If it's size, it's in bytes. Okay, there we go, wonderful. So now back inside our application, we create these, and we, instead of having indices in this case, we just have, rather the size of indices, we just have 3 because there's 3 indices in here. Yeah, look, I mean, if you wanted this to be automated, you could just do size of, because I know some people are going to complain, they always do, uint32t, right, like that. Just what I should use here. All right, and then that will give you the actual count, if you really want to do it that way. This will keep the same, and then, I mean, look, we probably need to bind it at some point. If I run this right now, it probably won't give us a triangle because this is a bit suspicious, and unfortunately it has been a while since I've used OpenGL. But we will see what we get here, if anything. Okay, so we get nothing, and we get a crash, in fact, inside the driver. Yeah, probably nothing's bound. I mean, we're trying to draw elements here. I bet we've got nothing to draw. So the other thing we need to do is actually use our, instead of just having 3 hard-coded here, we should get our index buffer and actually get the count. That's why I wanted it here. Okay, so let's fix up our buffers, because clearly I am not as good as I thought. We need to bind our buffer, which I guess means that why to use create, why to use gen, they're the same in terms of buffers. For like textures, you actually specify the target immediately. I kind of maybe thought that it would be like the same here, but I guess not, right? So this is the one for index buffer. So, you know, OpenGL is a bit inconsistent, even though it tries to be consistent. And the reason they have create now is just to match the shader API, which has GL create shaders, you know, create shader, and GL create program. But anyway, I guess we'll see. So that's why you should still use create instead of just gen, because that way your API is kind of consistent. Or rather, your like OpenGL's API is consistent. Let's run that and see what happens. And since we've bounded and left it bound, it should be in the vertex array now and everything should be great. And as you can see, it is. So hopefully that sheds some light as to all the blabbing I did in the beginning of the video where I was like, you know, you have to do this, you have to create all these classes. Now we've done that. You can see we have the base classes here, which are just interfaces with no data at all. And then at runtime, we make the choice to actually return a specific instance of a specific rendering API. Hope you guys enjoyed this video. If you did, you can hit that like button. You can also help support the series by going to patreon.com/thecherno. Your support is greatly appreciated and it is what keeps this series going. So huge thank you to everyone who helps support the series. Let me know what you think of this kind of design. Let me know if you've seen other designs that you think are better. This is the one that I've kind of been using for years, and to be honest, it's my favorite because all the decisions are made at runtime. And in terms of performance, like, I don't know, some people out there might be nitpicking, being like, but it's a virtual dispatch every time. It doesn't matter. Like, it honestly doesn't matter. I've done benchmarks around this kind of stuff. I have never been in a situation where I've written a game or an engine and I've been like, man, you know, I wish I had the extra performance that having non-virtual function calls would have had. I mean, not saying that that scenario doesn't exist. I'm saying in my experience and for what I'm doing and for what I'm trying to do with Hazel, which is going to be a very high performance, like quite demanding and visually demanding kind of engine, right? This kind of stuff definitely is not going to matter. If you're making some really small engine for like, you know, pixel graphics on like an embedded system, yeah, maybe this stuff would matter, but it doesn't for something like this. For homework, see if you can create the shader API like this, because right now I've got the shader class, but it's actually just OpenGL functions, whereas this buffer.cpp file has no relation to OpenGL at all, right? We include OpenGL buffer, but that's, again, only if we're on a platform that supports it. And also, we're not including GLAD or anything like that. And neither is OpenGL buffer, by the way. If you look at OpenGL, if we just quickly look at the buffer class, this doesn't include GLAD, right? The CPP file does. So we're never actually including GLAD into our generic buffer class, and we shouldn't, right? Same with kind of Directx. You usually don't want to do that. With Directx, it's probably okay, because you'll be only building that on Windows, but for something like this, we don't even need to. And if you can avoid it, you definitely should. And then the other one you can have a go with is Vertex Array, and just see if you can make that application class completely kind of generic. Anyway, I hope you guys enjoyed this very long episode. Been sitting here for like an hour almost. Next time, I think we're gonna either take more control with the renderer class, or I really want to also talk about Vertex Arrays and how they fit in and how we can abstract that, and maybe the buffer layout as well. But yeah, let me know what you want to see, and I'll see you guys next time. Goodbye.